Welcome to the next video in this lecture series. Today, we're going to be talking about how to summarize data. Specifically, we're going to be talking about describing data numerically and visually. This is part of the Applied Statistics Using Programming series brought to you by Sogang University. My name is Professor Ian, and let's get started. Describing data numerically and visually. What does that mean? Why would we want to do this? Well, usually when we get a new data set, maybe we have information about university students, or we have customer data for a company, or we have some survey data that we might have collected. In that case, we might want to briefly describe the data. Where is the average of the data? How much variation is there in what we're measuring? We might want to visualize it so we can see the distribution more clearly. This is usually one of the first steps when analyzing a data set. So this is the content that we're going to cover in this video. Before we start, let's talk a little bit about the terminology that we're going to be using a lot. An observation is a row of our data set. So if you think about our data frame as a table, like in Excel, an observation would be one row of that data. A variable is a characteristic represented as a column of that data set. A data set is all of the values that we have collected. So we may have different individuals. Those might be people, students, they might be companies. And we have characteristics of each one of them. Now, why do we put each observation as a row and each variable as a column? Each column represents a characteristic. Now, let's say I have information about students taking this course. I know this is an online course, so I don't really have grades, but you can imagine that you might have a midterm exam score, a final exam score. You also might have a grade at the end, an A, a B, a C. So each one of these columns would be one of these different characteristics, your score for your midterm, your final, or your grade for the whole course. Now, depending on your data set, you might have one column, one variable, or you might have two variables, or you might have 100 variables. So depending on how you're analyzing your data, we have different words for it. If we have one variable, we call that univariate data set. An example might be the grades for the course or income that you might have. Okay. Using univariate, there's a lot of basic statistics we can calculate, like a mean. We could get the average income, or we could get the standard deviation, how much the income deviates from that mean. Bivariate means we have two variables, bi meaning two, uni meaning one. So bivariate means we have two variables, and we could analyze the relationship between those two variables. When the temperature goes up, people buy more ice cream. Or when people get older, they generally earn more income. Okay, so an example of a bivariate analysis would just be the analysis of two variables, trying to understand how are they related. We can do scatter plots or correlation analysis to analyze two variables. Multivariate means there's multiple variables. There's three or more. In multivariate analysis, if we're trying to use these three variables or more, then we have multiple dimensions. If we have 10 variables, then we have 10 dimensions, and it's much more difficult to plot. It's very difficult to visualize 10 dimensions, but it's much easier to analyze it statistically. So for example, using regression modeling, which we cover towards the end of this lecture series, then we can easily understand 10 dimensions in a numeric way, in a quantitative way. As we mentioned in the previous video, there are several different data types in R. Categorical variables are usually called factors in R. Numeric variables are usually called numeric if they're continuous and integer if they're discrete. There are several formats to data. One of them is time series data. In time series data, each observation in the sample represents a different equally spaced point in time. So for example, if you have a stock price, you might be looking at that stock every day, or every month, or every year. The periodicity is the time between observations. So for example, is it daily? Is it annually? For time series, we usually use time series to try to understand trends over time. Is something generally increasing or generally decreasing? It can also be used for understanding patterns in time. For example, when do most Koreans go to the Philippines? Is it in the summertime when it's very hot? Is it in the winter when it's very cold in Korea? That would be an example of seasonality. During specific seasons, people tend to do the same behavior, especially when it comes to traveling or purchasing behavior. Cross-sectional data means that each observation represents a different individual unit, a person, a company, at the same point in time. For example, right now, what is everybody's height? Or at the end of the year, what is everybody's weight at that time? That would be a cross-sectional data set. For cross-sectional data, we're interested in variation among observations. How do the individuals vary over the data? So for example, is there a big difference or are they very similar? And relationships between variables. Is there a relationship between these two variables, height and weight, for example? It's called cross-sectional because if you think about it over time, it's like you're cutting a slice of bread. It's like you're cutting a piece of time out and analyzing the data at that point in time. Levels of measurement refers to how much information are we recording when we measure something. Okay, so there are a couple questions we can ask. The first one is there a meaningful 0 point? If yes, if there's a 0 that means 0, there's nothing, then we can do statistical operations, such as multiplication, division, making percentages. Are the intervals between scale points meaningful? In other words, is a 1 to 2 the same as a 2 to 3, the same as a 3 to a 4? If yes, then we have interval data, and we can use common statistics like the average or the standard deviation. Do scale points represent rankings? Is a 1 lower than a 2? Is a 3 lower than a 4? If yes, we have ordinal data. It's restricted to non-parametric statistical tests. We can do statistical tests on it, but we're limited in which tests we can do. Finally, are there discrete categories? If yes, this is one of the most basic levels of measurement, then we have nominal data, where only counting is allowed. We can only count how many are in each group. Let's talk about these in a little bit more detail. Nominal is the lowest level of measurement. Nominal, nom, meaning name, is just identifying or naming categories. They are qualitative, attribute, categorical, or classification data. So for example, one is not better than the others. They're just different groups. So for example, I'm American, my wife is Korean. None is higher or lower, or better or worse than another group. They're just different groups. They're different categories. They're different names of groups. They can be coded numerically, which is sometimes tricky to students who are new to statistical analysis. So for example, if we had some different airlines, Delta Air, Korean Air, Jeju Air, and I saved that data into a data set, and I said, Delta is 1, Korean Air is 2, Jeju Air is 3, some other airline is 4. It doesn't mean that one is bigger or lower or smaller or better than the other. I'm just assigning a number to that group. So we should remember that if it's a number, but it's a nominal measurement, like 1 is delta, there's no meaning to making an average. What's the average between a list of airlines? Is 2.5 meaningful? There's no meaning there. So nominal measurement just means that you have names of categories. The only thing we can really calculate is the frequency, how many times each group appears in our data. Ordinal measurement is a little bit more information in that it's named groups, same as nominal data, but we add one more characteristic, which it can be ranked. One is bigger or smaller than the other. One is better or worse than the other. One is faster or slower than the other. There can be a ranking system involved in ordinal measurements. The distance between codes is not meaningful. So in other words, what do you want to eat for dinner? If you want to eat chicken and maybe pizza, and maybe hamburger, let's say you ranked them in that order. Chicken is what you want most, pizza is next, hamburger is last. In that order, which one is best? Chicken. Is it the same distance from hamburger to pizza as pizza to chicken? We don't know. There's no distance measurement in an ordinal data. There's a ranking, but we don't know if one is very close, a second place is very close, or the second place is a really big distance after the first place, right? So distance is not meaningful if we have an ordinal measure. What does ordinal mean? Ordinal means we have an order to it, a ranking. There are many useful statistical tests, and ordinal measures are often used in social science. Interval measure is similar to ordinal measurement in that it can be ranked. However, we have now a meaningful interval between scale points. In other words, 5 degrees hotter is 5 degrees hotter. So for example, 15 to 20 degrees Celsius is the same difference as 20 to 25 degrees Celsius, right? A 0 point is arbitrary. So for example, if you say that it's 0 degrees outside, does that mean that there's no heat? No, 0 is arbitrary. We just say that 0 is the freezing point of water. And not only that, it's the freezing point of water at sea level, right? So it's very specific, but it's arbitrary because 0 in Fahrenheit doesn't mean the same thing. That means that it's arbitrary. It doesn't mean that there's no degrees, there's no heat. It means that there is an arbitrary point that we refer to as 0. Now, what's the difference with a ratio measurement? A ratio measurement is all the same properties of nominal and ordinal and interval. We have ranked, we have a meaningful distance, and now we have a meaningful 0. 0 means 0. If you have 0 money, that means you have no money. If you have 0 apples, that means you have meaningfully 0 apples. So what about a Likert scale? A Likert scale is something like this. Do you like this class so far? You strongly agree, somewhat agree, you don't agree or disagree. What kind of measurement is this? Is this a ratio? Well, there's no 0 point. And if there was a 0, it's not meaningful. So it's not. So is it an interval? Is there a ranking? Well, yes, excellent is better than good. Strongly agree is better than somewhat agree. So there is a ranking. Is there an interval? Is it the same distance between strongly agree and somewhat agree as it is from somewhat agree to neither agree nor disagree? Most statisticians would say, no, this is ordinal data. However, it's difficult to deal with ordinal data. So actually in social sciences, oftentimes Likert scale is treated as interval data, even though technically we really only have a ranking. We don't know that that ranking has the same distance between every point of your Likert scale. Okay, so visual summary is charts and graphs, whereas a numerical summary is statistics. So let's talk a little bit about each one. Specifically, let's talk about numerical summary. A stem and leaf plot is a bit of a mix between a visual and a numerical summary. A stem and leaf plot looks something like this. We have a column, 0, 1, 2, 3, 4, 5, and then we have our leaves. Here's our stem, here's our leaves. What does this mean? It means that we have different values and all of our data is being shown. So what is the maximum value here? Well, we have 5 in our stem. 5 is the biggest, and our biggest leaf is 9. What does this mean? This means this is the number 59. Next we have the number 50, that's 50. Okay. Underneath, what are the leaves in 4? We have 4, 2, that's 42. Under that we have 3, 8, 38, 37, 37, 31. This is showing all of the values. The stem is the tens place and the leaf is the ones position. These are very useful if we have a relatively smaller data set and we want to look at all of the values on our data set. We can also generally see some kind of a shape to our data, a distribution to the data, but it's a little bit vague. It's a little bit hard to see. We can see how many are in each tens area, but it's not technically a visual summary. A dot plot is also useful to see each individual in our data set. Each dot represents one individual, usually, and it's easy to understand. You can understand each individual observation that's being measured. Here we have PE ratios, so each dot would represent a company. Down here we have single family homes, so each dot would represent a single family home. They're easy to understand, and it shows you the dispersion, whether all of the values are clumped together in one place or if they are spread out. It shows you the shape of the distribution, and it shows you the central tendency. Where is the average or where is the middle of your data? However, it's very difficult to use if your data is very large. If you have 2 observations with the same value, you stack them on top of each other. So in that case, we can see the distribution much more clearly for each individual in our data set. It's good when you have a smaller data set. A histogram is good for a lot of different things. Specifically, it shows a frequency distribution. A histogram, you'll see that each bar is connected and you have a continuous number. So for example, scores to a test, or in this case, a PE ratio, which is used in finance. A frequency distribution is a table formed by classifying n data values into k groups. So the classes, or the bins, are the groups that we're stacking up, the frequency of people falling within a specific range of that x variable. Okay, so for example here, we have about 24 companies that have a PE ratio between 10 and 20. We have about 11 companies that fall between 20 and 30. Okay, this is how you can read a histogram. It's a graphical representation of a frequency distribution, how many observations you have within each range, within each bin. Okay? It's very useful for numerical data, specifically for continuous data. The y-axis shows the frequency, or how often it occurs. The x-axis shows each bin, the endpoints, the tick points. Okay? So, using the same data, we can look at our data a little bit differently depending on how many bins we have. Our data might look a little bit different, right? So this is the same data using 6, 8, or 9 bins. Which one is best? Well, bin limits define the values to be included in each bin. So for example, you can see with 8 bins, each bin is a smaller range of values. With 9 bins, we have even smaller range of values. The width of bins should generally be the same. In other words, in our first example with 6 bins, each bin is 10. So 0 to 10, 10 to 20, 20 to 30, 30 to 40, and so on. Our next one, the width is also the same. We have 0 to 8, 8 to 16. Each bin is a width of 8 PE ratio. Okay, and the frequency or the number of observations in each bin. How many observations are within that range? There is a specific rule for setting the number of bins. Okay, so that is called the Sturge's rule. In other words, if you have a sample size of 1, you should use 1 bin. If you have a sample size of 8, you should use 4 bins. If you have a sample size of 128, you should use 8 bins. Why is this important? Because by default, in R, when you use a histogram, it uses the Sturge's rule to estimate how many bins to use when you use that function. All right, so what is a modal class? A modal class is a histogram bar that is higher than those on either side. It's a peak in your distribution. Unimodal means you have 1 peak in your distribution. Bimodal means we have 2 peaks. Multimodal means we have multiple peaks in our distribution. Modal classes may be the result of the way bin limits are chosen. So depending on how many bins we might have a different number of peaks in that distribution. We also have shape. The histogram suggests the shape of the population. It's influenced by the number of bins. Skewness refers to the unequalness of each side of the data. Okay, so left skewed means you have a long left tail. Right skewed means you have a long right tail. Symmetric means your distribution is equal on both sides. Outliers means that you have some individuals that are very far from the central tendency of your data. In other words, you might have a value that's very far from the average of your data. We call that an outlier. We'll cover this in more detail later. So here we have some examples of different skewness. So here we have a left skew, like our distribution has a long left tail, or we might have a long left tail with 2 humps with 2 modes. We call that bimodal because there's 2 bumps in our data, and it's skewed left because we have a long left tail. We have the same thing on the right if our data looks like this. So these are different ways that we can describe how our data is shaped. This gives us a better idea of what the circumstances or behavior is of the observations that we're measuring. Line charts often are misused, but line charts should generally only be used for time, over time. So it's used to display time series. It's easy to spot a trend or compare time periods if we're using a line chart. They can display several variables at once for easy comparison, such as this 2-scale line chart on the bottom. A 2-scale line chart is used if we have the magnitudes. What we're measuring is different between each line. So for example, we have the minutes per call and the dollars per month. We have 2 different scales, and we have 2 lines. Each one is related to a different scale. So the average call length is using minutes per call. The average monthly bill is using dollars per month. We can still compare these even though they're using different scales. A log scale is used when something is compounding using an annual percentage. So for example, a stock portfolio, if I have $100 and it increases 10%, now I have $110. However, if I have $1,000 and it increases 10%, now I have $1,100. So even though that increase is much bigger, $100 compared to $10, if I use a log scale, I can compare the percentage changes. Both of those examples is just a 10% increase. All right, column charts, bar charts, and pie charts. Column charts and bar charts are basically the same thing. Column charts are oriented as columns. Bar chart is oriented as kind of rows of bars, right? Okay? They're used to show categorical data and the frequency of each category existing. There are many variations on bar charts and column charts. One of them is stacked bar charts, which means you're looking at two variables together. The total can be looked at, and the difference between the proportion can also be looked at over time. Pie charts, I recommend not to use. I know they're very common, they're very colorful, it looks fun, but actually it's a little bit difficult statistically if you have two groups that are very similar. So a pie chart is a way to convey a general idea of the data. Pie charts are good to portray data which sum to a total, so the total should be 100%. If the total is not 100%, you probably don't want to use a pie chart. A pie chart should only have a few slices so that it's easy to tell the difference between the groups. Each slice can be labeled with a value or a percent to make it a little bit easier to understand how big each group is. I would always recommend to use a column or a bar chart instead of a pie chart, but I know pie charts are very common, so we should understand a little bit about how to use them. Okay, so as I said, I don't like pie charts, and here's why. On top, we have a pie chart. On the bottom, we have a bar chart. It's much easier to compare directly the difference between those. On the top example, the blue and the red look quite similar. But if we look at a bar chart, the blue and the red look quite different. Okay, so you can show the same information using a bar chart as you can a pie chart. I don't think this is the best example of a bar chart because generally you should list your bars from biggest to smallest, or possibly from smallest to biggest if that's what you want to show. Because then it makes it much easier to compare which group is biggest and which one is smallest and the ranking between them. Whereas in a pie chart, it's a little bit more difficult to understand, and in a bar chart that's not organized, it's also a little bit harder to understand which one is the second or third or fourth group. Scatter plots show a relationship between two variables. In this case, we're showing the relationship between life expectancy and birth rate. They can convey patterns in data pairs that would not be apparent from a table. A scatter plot is a starting point for bivariate analysis. In other words, what is bivariate? It means two variables. So if you're trying to analyze the relationship between two variables, you should usually start by just making a scatter plot so you can understand the relationship between them. It doesn't mean that it's a cause and effect relationship. It just means that it's showing you the relationship. When one is bigger, how does the other variable? Is the other variable generally bigger or smaller? So for example, if you look at height, people who generally have a higher height also generally have a higher weight as well. How strong is that? Depends on what data set you're looking at. All right, here's some examples of different relationships. So you might have a positive relationship. So as x increases, y also increases. In that case, you get a strong positive relationship. Strong is referring to how close the data is. If If the data is closer to a line, it means that there's a stronger relationship. If the pattern is weaker, in this case we have no pattern. In the case of no pattern, there's no clear line up or down. We can't really tell. That indicates that there's no pattern. However, we may also have a nonlinear pattern, such as an arc. In this example, a scatter plot is easy to show that relationship. Okay, so when we are making visualizations, we should consider some errors that people usually make. The first one is, should you include 0 or not when you're scaling your y-axis? The second one is the proportions of your graph. If we stretch it out, it might look a little bit different than if we scrunch it up. If our y-axis is very long scale, we may look at it differently than if we had a shorter scale. Consider what kind of titles or pictures you're using alongside your graph or your visualization. I would recommend against using novelty graphs. Novelty graphs can be distracting if you're using different graphics or three-dimensional graphics when you don't need it. It can be distracting and sometimes difficult to interpret. Rotated graphs, so instead of a column-wise, you might consider using a row-wise, right? The difference between a column chart and a bar chart. Complex graphs that are too complicated are sometimes difficult to read. The area trick is when you're using something like a pie chart, sometimes it's difficult to tell exactly the difference between magnitude of two groups if we're using the area within it to measure how big it is. So let's look at some examples in R. I think it's much easier to look at some examples using R than to just describe the theory in general. So let's switch over to R. Okay, so here we started our R session, and let's look at some examples. My first example is looking at categorical variable. So categorical data, if you can remember, we use as a factor. So let's make some data, car, truck, subway, car, subway. We have some different groups in our data. Now let's change that into factor data. And now let's check the class of our data. What type of data do we have? Factor, that means we have groups. Levels tells us what are the possible groups. Car, subway, or truck. We only have 3 groups. Table will tell us how many are in each category. 3 means there are 3 cars in our data, 2 subway, and 1 truck. We can also plot if we use the function plot and input our factor data. R will automatically create a bar plot for us. Okay, so this is showing us that car, we have 3 values, subway, we have 2 values, and truck, we have 1. So our data looked like this. We have car, truck, subway, car, subway. Now, what if I took our same data, let's call this one variable coded, we're going to code our data as numeric. In other words, what that does is our data now looks like this: 1, 3, 2, 1, 1, 2. What does that mean? What is 1? 1 is referring to a car. 3 is referring to a truck. 2 is referring to a subway. Okay, if I turn that into a factor, now we check our data, it's still a factor. We check the levels. Now our levels are 1, 2, and 3. If I make a table, it tells us that in group 1, we have 3 values. In group 2, we have 2 values. In group 3, we have 1 value. Then if we plot this, we see group 1, we have 3 values. Group 2, we have 2 values. It's the same result because it's the same data, but it can be confusing if you're coding your categories with numbers instead of words. Okay, so this is an example of doing the same thing, but if you coded your categories, it might be a little bit difficult to interpret. Okay, now let's say there is a survey question and there is only 0 meaning no, 1 meaning yes. That's our data. I'm going to change that data to logical, meaning true or false. And if we check our data, the class is logical. If we make a table, it tells us how many people answered true and how many people answered false. And if we plot this result, so we get something very difficult to read. What is this telling us? Well, on the x-axis, we have index, and on the y-axis, we have 0 and 1. So I'm trying to show you what not to do. If you try to plot it like this, it's going to be very difficult to understand. Your index is saying your first value is a 0. Your second value is a 1. Your third value is a 1. Your fourth value is a 0. Okay, so if you end up with something like this, this is probably not what you want to do. So, in other words, I would recommend not to use logical, but in other words, to use a factor because it's much easier to plot. So this plot function predicts, based on the type of data that you have, what would be the best way to plot that data. Sometimes it does a good job. So for example, with the factor, it does a good job. But if we're trying to plot something as logical, it's not very good at doing that. All right, so next, numeric data. Let's say we're plotting discrete data. We're plotting an integer, 1, 2, 3, 10, 100. There we go. This is numeric data. We call it an integer. So if we check our class, it is an integer data. If we print our data, looks like this, 1, 2, 3, 10, 100. What's going to happen if we plot this? We get that same strange result where on the x-axis we get the index. The first index is around 0. Second one is about 1 or 2. Third one is here. Fourth one is here. If you're plotting a vector, an integer or a logical true or false result, sometimes it's a little bit difficult to read because the x-axis becomes the index, which is a little bit confusing. If you have continuous data, let's just run all of this. We get the same result, right? Okay, so any numeric data type, I would recommend is probably you don't want to use plot, but you might want to use one of the other functions that we're going to introduce in a minute. All right, next, level of measurement. So here, let's say we have a list of people coming from different countries. We have nominal data, right? Here's our nominal data. If we check the class, it's a factor. If we check the levels, we have levels. There's no ranking to these levels. It's just different groups. If we have ordinal data, let's say we have A, B, C, and F. Well, an A plus is better than an A B plus is better than a B, and better than an F, right? So we have a ranking here. We can use this function factor. Here's our data. And ordered true means that we have an order. So this means we have ordinal data. By writing our levels, we can say the order that we want. A plus is the best. A is next. B plus is next. Okay. So in this way, we have an ordered factor. In R, an ordered factor means we have ordinal data. If I check my levels, it will show them in the order, A plus being first, F being last, right? Okay. An interval measurement. If we have an interval measurement, let's say we have Celsius and Fahrenheit. These are the same values in Celsius and in Fahrenheit. So this last line of code is not useful, but it's showing whether the change is consistent between the interval of Fahrenheit and the interval of Celsius. I think it makes more sense if we look at our second example. So let's say we're looking at Sunny's height. And the first one, we're looking at centimeters. The second one, we're looking at inches. The last one, I think we're looking at miles or kilometers or something crazy. Okay, so I have the same height listed in three different measurement systems, right? Centimeters, inches, and miles. Okay, next, the basketball star Seo Jang-hoon. I have him. I'm not sure how accurate these numbers are, but this is his height in centimeters, in inches, and in miles. Miles are really long, right? It's like 2-point-something kilometers. All right, so if I round the difference, what is the difference between her height, Sunny's height, and Seo Jang-hoon's height? If we check the change, it's consistent across all three different measurements. So it's the same difference if we're using centimeters, or if we're using inches, or if we're using even miles. The difference between those two heights are consistent. So that's why a ratio measurement is so much more useful than an interval measurement, because we can measure something and the difference is consistent, and it doesn't matter which scale we're using. If we're using inches or centimeters or kilometers, it doesn't matter. Let's look at a stem plot in R. So here's our data. We have PE ratios, right? And here's a stem plot. Let's make a stem plot and try to understand it. Here is our stem plot. It tells us the decimal point is 1 digit to the right of this. So in other words, this means that we have PE ratios. So this would be 0.7, 0.9. Over here we have the stem, 1. So that means these leaves are each observation. So we have 1.0, another 1.0, another 1.0, another 1.0, 1.1, 1.2. So this would be what? This would be 4.2. That's how we can read a stem plot. And it shows us the distribution generally. Okay. So stem plot can be very useful, especially if we have a small amount of data. We can also make this dot plot. So here's a dot plot in R. I tried to copy the same visualizations from the book, but using R instead. Okay, so this is how you might make that. So here's our data. We're using a stacked method, so each dot on top of each other. If we have two dots at the same point, we stack them on top. And the rest are visual changes. So make it sky blue, use point character 16, meaning they're dots with filled in circles. This at 0 means that we're starting at 0. It's at the very bottom of the plot. If we delete this, run our code again, we get the same result, but it's not at 0. It's about halfway in the middle of our plot. So it's a little bit difficult to read. So I like to add that at 0 to make our plot right at the bottom of the plot. So that makes it a little bit closer to our x-axis, makes it easier to read. And in R, I can take my data and scrunch it down, can run my plot again, and it'll create that same plot in the new size of my plot. Let's change the size of my plot again. Looks a little bit ugly, so let's run it again, and it'll create a new set based on the size of this visualization window. All right, next. Here's the same data again, but in this case, we're going to make a histogram with that same data. There's our data. All right, so here's our histogram, 0 to 10, 10 to 20. And here we see, here's my data. Right equals false means that if a value is on the breakpoint, so for example, if the value is exactly 20, should it go in the left bin, 10 to 20, or should it go in the right bin, 20 to 30? Right equals false means it's going to go into the left bin, right? All right. If we want to change the number of bins, we can use this argument called breaks. Breaks equals 5 means it's going to break our data up 5 times. that gives us 1, 2, 3, 4, 5, 6 bins. Where are the breaks? One's broken here at 50, broken at 40. It's breaking the bins 5 times. So 10, 20, 30, 40, 50 is where it's breaking into 6 bins. Here we have 8 bins. We can break at specific places, so I'm going to break at specific locations just to show you a different way to do it. Here the first one is 0, the next one is 8, the next one is 16. So this is just following the same method that was used in the textbook. So here you go. Here's 8 bins. Here is 9 bins. We see that with the same data, we can change what it looks like by changing how many bins we have by using this breaks argument. Next, let's look at those line charts. Let's try to copy those line charts into R. So here we have 2 sets of data. We have our rate and we have our year. Okay, so here's an easy line plot. We just use the function plot. Here we have our x-axis and our y-axis, and this says type equals L, L for line. And there we go, we get a nice line plot. Now, that one's not very pretty, so we can add some extra things using arguments. So again, we're using plot. We have x, the year, y, the rate, type equals O. That means it's going to put a point for every value of our line plot. Main is the title, so we can add a title. YLab is the label on the y-axis. XLab is the label on the x-axis. In this case, there's just nothing there, so there's no label on the x-axis. Y-limit means the y-axis goes from 0 to a maximum of 50. The line width, meaning how thick our line is 1.5. So it's 1.5 times the normal default line. Point character 21 is just a different shape for drawing the dots. CEX is the size of those dots. Color is Dodger blue. This is just a color I like. BG is the background color. I'm going to make it a red color that I like. So let's run this here and see what our plot looks like. And it looks like that. That BG is the background of inside our circles. Again, I tried to copy as closely as I could what I saw in the example in the book. That's what this is. All right, we're almost done. Next, we have a column and pie chart. So let's say our data looks like this. We have companies and we have percentages. All right, so here's our companies. Here's our percentage of market share for each one of those companies. Let's draw a bar plot. Here's our bar plot. In R, if it's too small, we can bring it out and it'll fill those in for us. Okay, so here is what that looks like. So using a bar plot, or what we might call a column chart, using a bar plot like this, we can easily see which company has the biggest market share, Goodyear. And these 3 look very similar, but if we sort it into a bar plot, we can see very easily which one has a little bit more market share out of these 3. You can also see the difference between these as well. If we make a pie chart, it's much more difficult to tell. So here's a little bit more advanced bar plot. So what are we changing here? Here we have the height, we have the names, these are the categories. LAS means the angle that we show the words. Let me plot this and point that out. Okay, so LAS means write these company names. Angle number 1 is horizontal, angle number 2 is vertical. So write the names vertically. Make the axis 1.5 times bigger. So make the margin a little bit bigger and make the names a little bit smaller, 0.75. So make them 3/4 the size they normally are. Make the axis title in navy color. So we can see this is actually navy color. The column main, that is the main, let me put this over here. That is the main title, we made it purple. So you can see we added some titles and some y-axis labels, and we changed the color of some of those. Okay. All right, cool. All right, here's a bar plot using the same information, but this time we're using the horizontal equals true. That means we're going from a column chart to a bar plot because it's row-wise. Bar plot. So here, if we tried to make that look a little prettier, we might change it, make it look a little bit like this. And we could kind of adjust that to change what that looks like. Okay, cool. All right, so let's do the same thing with a pie chart. Here's our pie chart. And now it becomes very difficult to tell which one of these is bigger, Dunlop, Continental, Uniroyal, Bridgestone. It's very difficult to tell when we're looking at a pie chart. But actually, in R, it's drawing the pie chart in a specific manner. So it's drawing it from here, from the 3 o'clock position, counterclockwise. So that means that this Goodyear is the biggest, Firestone is second, Michelin is third, all the way to Dunlop, which is smallest. Okay. So it's difficult to tell, but we can still see a little bit of a ranking there if we understand how R makes that pie chart. And we could change the colors of our pie chart, make the border white. So if you wanted to change the colors, you could do it like this. Okay. All right. Finally, let's look at scatter plots. Scatter plots, as we just said, show the relationship between two variables. Let's plot. Here we go. This one is just saving those variables. Here we have the life expectancy in several different countries and the birth rate in those same countries. If you wanted to know how many countries we have, we could use that length function. And our variable is called var birth rate. So let's just check. That tells us that we have 153 values in our data set. Let's go down. Let's plot the relationship between life expectancy and birth rate in each country. All right, so we see that as life expectancy gets bigger, the birth rate is lower. So if life expectancy is very large, the birth rate is very low, right? We can see that in Korea and Japan today, right? So let's clean that up a little bit, make it a little bit easier to read. All right, so here we changed each point from a circle into a square. That way we can kind of see a small difference if there's two that are almost right on top of each other because the points of those squares are a little bit different. Okay, so that makes it a little bit easier to read. Not great. CEX is the size, PCH is the type, so 18 is a square type. The color is sky blue. This is showing you the limits, so this means X is from 30 to 90, Y is from 0 to 60. And these are adding labels to the X-axis and to the Y-axis. All right, so there's one thing that's cool in R. When we're plotting in R, we can use this identify function. And what that's going to do is when our plot windows open, it allows us to identify what are these little points in our data. So let's plot our data. Here's our data. I'm going to make it a little easier to read, just make it bigger. And next, I'm going to use this identify function. Let's run this. And now you'll see when I click on the image, it tells me which index number that is. Now, if I had the names of countries, I could add the names of the countries and I could identify them by clicking. In this case, I don't know which country is which, I just know the index number. So this one is just showing me the index. Country 74 is this point here. Country 68 is this point here. Again, I don't have a list of the names of the countries, so I'm not sure what that number indicates. But if we had a list of the names, we could show those names here using the identify function. Cool, so that was an explanation of how we can kind of copy some of those figures we see in the textbook, but using R. You can play around with this code a little bit, maybe change the color, change the CEX to show bigger or smaller points, change the PCH to change what style those points are. Just play around with it and you'll be able to understand how this code works a lot better. Okay, cool. See you guys in the next one. Goodbye. Now, depending on your data set, data set,